Good evening everyone. I am Nikhil Jain from Department of Electrical and Electronics Engineering. Today I am presenting my internship project completed at Emertxe Technologies. The title of my project is Real-Time EV Dashboard and ADAS Warning System using STM32 Blue Pill board. This project combines embedded systems, battery monitoring, UART communication, and a Python-based dashboard to simulate how modern EV vehicles monitor their health and warn drivers whenever unsafe conditions occur. The embedded systems training and development company, which built me more knowledge about the embedded systems. During my 1 month internship, I worked on embedded project based on EV vehicle technologies. The main skill I learned are embedded C programming, STM32 microcontroller programming, UART serial communication, PICSimLab simulation. The objectives of the project mainly focuses on some important parameters like battery voltage, battery current, battery temperature, vehicle speed, state of charge and driver warnings. In any of these parameters cross their safe operating limits, the driver must immediately be informed. The objective of our project was to design a simplified EV dashboard that continuously monitors these parameters and generate warning messages whenever unsafe conditions occur. Instead of using expensive automotive hardware, we implemented the complete system using the STM32 Blue Pill microcontroller and simulated the entire vehicle inside PICSimLab. Although this is a prototype, the working principle is similar to commercial EV dashboards. Hardware architecture. The heart of our system is the STM32F103C8T6 Blue Pill board. It is based on ARM Cortex M3 processor running at 72 MHz. The controller provides 64 KB flash memory, 20 KB SRAM, ADC, timers and GPIO. We selected this because it provides sufficient computational power. In our project, STM32 generates simulated sensor values, processes them, checks safety conditions, finally transmits the processed data through UART. PICSimLab. I used the core software called PICSimLab. Instead of repeatedly programming a physical STM32 board, we first tested the firmware inside the simulator. The advantages are faster debugging, no hardware damage, easy testing, UART communication testing. If there was any error in firmware, we corrected it inside the simulator before testing on hardware. Firmware flowchart. This flowchart gives the total idea about the project. Initializing the STM32 initializes the clock, GPIO pins and UART communication. Sensor reading. It generates simulated EV sensor values. Processing. Sensor values are validated and filtered noise and improves the accuracy. Threshold check. The values are compared with safe operating limits like even battery temperature, voltage, obstacle distance, any warning logics. UART transmission. All processed values are packed into UART packets and transmitted to Python dashboard to simulate the output. The BMS, one of the most important slide is that to understand the BMS of the EV vehicle. In our project, it continuously monitors the battery voltage, battery current, temperature, and state of charge. State of charge indicates the remaining battery percentage available to the driver so that he can calculate the range of the vehicle. 100% means it's fully charged, like 20% means below battery level indication. If battery voltage becomes too low or battery temperature becomes too high, the dashboard immediately generates warning messages like high temperature and engine heatage. Python dashboard is like graphical representation of my project. The STM32 continuously sends the sensor values through UART. Python receives the data using PySerial library. The received packet is decoded and the dash callback functions automatically update the gauge, graph and warning indications. Here are some pictures that I have uploaded about the vehicle speed, battery state of charge, like many other parameters like time, average speed, and here you can notice the power, current, steering angle, how the driver is rotating, like cruise control, many parameters like driving gear, driving sports mode, and this is the ADAS safety check. Like any obstacle is incoming, it gives the notifications or it displays on the ADAS system. UART protocol stands for Universal Asynchronous Receiver Transmitter. It communicates between the STM32 and Python. We selected it because it was simple, low cost, and mainly focused in our internship was about the UART. They explained about this very smoothly. Each UART packet contains header, upload, checksum, footer, and the detect communication error. The dashboard charts I will show you now in a few minutes. I will simulate in Python dashboard and show the output. The temperature gauge changes color according to the temperature, warning indications and battery voltages. Everything will be shown in the Python dashboard. Like this is the simple real-time data flow, like how it works, like sensor to HTM, UART, Python and driver. The UART transfers the data, Python receives and decodes it, dashboard displays the information, STM32 processes it to UART. This is the main theme of a project, that ADAS warning logic. ADAS stands for Advanced Driver Assistance System. Our project implements a simplified ADAS system. This system continuously checks all incoming sensor values. Whenever parameter crosses a predefined threshold, a warning message appears. And here is small photo of how ADAS works. It has blind spot detection, collision warning, sound view, surrounding view, parking assistance and any other incoming obstacles like over temperature warning, low battery warning. In real vehicles, ADAS also includes lane assist, automatic braking, adaptive cruise control. Fault handling. No embedded system is incomplete without any fault handling. Even in power systems also we handle many fault handlings and improve the reliability and the working. Our project continuously monitors the UART communication error, invalid sensors, timeout conditions, and whenever such fault occurs, the system detects and improves the reliability. BMS algorithm. Our project uses simplified BMS algorithms which include SOC estimation, battery health monitoring, remaining driving range estimation, and I included a lot of parameters to detailedly understand how the ADAS and real-time EV monitoring system works in the car. Like these are the Python backend graphs which I have obtained while doing the demo of the project. Like it detects the collision warning and system health, and this is the spikes occur when the incoming collision or any obstacle. All the dashboard gauges and graphs are updated automatically. This is the conclusion of this PPT, and now I will show the simulation of the project. So this is somewhat lengthy. This is the main C code which I have used in the EV ADAS and monitoring system. This main C contains the EV control and the incoming objects and other parameter like battery temperature, warning collision, overspeed, and here this also sends the UART communications to easily understand the errors if there is any error in the code. here the EV control code the uh, this is used for the acceleration, braking pedal, motor speed, and have defined many parameters and constants like maximum speed, the battery capacity, dragging efficiency. UART it here the UART is initialized for the communication protocol between the STM32 and the Python. This is the main H including main H program which like defines this STM32 billboard. Each of the syntax that I covered is particularly single parameter I have coded in this so to get the defined output like gear indication like a right indicator, left indicator, driving mode like sports mode. It shows under the eco mode, it shows the normal. If the speed is above 80, it shows the sports mode. Steering angle, like this is the formula of the steering angle. Like this have initialized the many parameter obstacle distance. Now we'll run this project. I have created this project as 0 errors and 0 warnings. Now I will simulate in the PICSimLab using blue pill board. So this is the output of the project. See, like this it has many simulation cycles like say, starting the it checks the battery management system, motor control, UART communication. Initially the vehicle speed will be in null position, so the cruise control is off and gear is in parking mode, the driver is eco. Like after some certain speed the vehicle starts accelerating. It shows the battery parameter, battery state of health, voltage, current and power, energy, trip distance, the odometer. Like we can change the odometer here based on our utilization. And steering angle, like I have basically added the major frequently used angle, how it starts, and the indication like left and right. It depends on the driver axis. After some certain speed you can notice that the here it's showing that blind spot is clear and active vehicle centered. After some certain speed the obstacle will come near to the vehicle. It gives an indication to the driver. We can see in after 2 3 simulation cycle like it detailedly shows that certain speed like 30 35 40. See, it shows the now it shows the warning collision forward and like any obstacle is incoming, it detects and it gives a notification in the ADAS system. And we can see the driver like I have added a new parameter like driver score, which how he controls the vehicle. See, the automatic braking will be applied if the driver is on any some unconscious mode or something. It it can calculate the obstacle distance also. Like obstacle is near very like it's near the 32 centimeter. Emergency brakes will be applied. The more the obstacle is near to the vehicle, it applies the emergency braking and clears the lane. Like it moves to the next clear safer lane. Now we can see the braking has been on automatic braking mode. The driver's code will be decreased as it has detected the ADAS system. Now the speed is above 90 and the average speed is 50. the mode will be switched to the sport mode, and if there is any obstacle incoming, the automatic braking and emergency breakers will be applied. uh, by by increasing the temperature, the motor heating also increases, and it signs the driver that some issue is in the, like it's issue in the motor's engine. Here we can vary the, like vary the temperature of the car or engine. Again, it decreases the speed after the, like forward collision has been detected. It decreases speed automatically, and the driver score will be also, like it's a new parameter added in the project. The driver score will be reduced, and it gives some certain rating. So this is the, like output which I got in the simulation. Now I'll same demonstrate this one in the Python dashboard. This is the Python dashboard file. Python. Like this installs the dashboard and PySerial. Here we can notice that I have already installed this like before doing the project. Now I will show you the simulation of the real-time data. See, this is the demo of the working of this project. It is running in this server. Now I will check this one in the web. Now you can see the output of the project. It continuously detects the real-time information how the vehicle is running. This is the battery state of health, and the obstacle distance, like it detects the obstacle, how much far is it is. Now you can see the motor temperature. As I can increase there, the motor temperature will be affected here. This is the final EV dashboard developed using the Python dash. It receives the real-time data like from the Blue Pill board through UART. This is the main vehicle speed gauge. The if the speed is above 80, it shifts to the sports mode, as you can notice here. As it reduces below the 80, it goes to the normal eco mode. Normal and eco. See, like distance obstacle is very near, the ADAS system indicates is the emergency, and the graph will be spiked here. As the distance is slow, the emergency brakes and will be indicated. This is a system health, like it's the normal that the driver score also will be updated in particular state. The simulation cycle shows how many cycles the firmware has executed. The time indicates the elapsed running time. Average speed gives the average, like simulation speed. The motor parameters are like motor temperature, controller temperature, and this is the, like some random GPS I have included. Like if you want any particular GPS, we can install to it. The headlight, and these are the basic parameters: headlight, steering angle, cruise control. Cruise control will be best on the 80 kilometer per hour. Cooling fan, like when it's above the engine is more heated, the cooling fan will occur. So yeah, this is the main project I have worked on, the real-time EV dashboard developing. So here we can see the, again it will be continuously running. The cycle will be continuously running after the certain speed it has been reached. So yeah, in the conclusion, I would like to say that the internship project successfully demonstrates the integration of embedded firmware system. The Blue Pill performs real-time data generation and testing and debugging. The project demonstrates simplified battery management concepts and ADAS warning. Basically, it detects the ADAS warning. Like this is the main motto of the project, to detect the warning informations and the ADAS system. Like many upcoming vehicles are using the ADAS system to, like, which stand aside in the market to gain more attraction. The overall project improved both my embedded system knowledge and practical implementation. Like I was very happy to learn this information about the how to use embedded systems and how to apply it into the PICSimulation lab and demonstrate in Python. It was very interactive way and good to learn these new things. And yeah, this was the fine. And you can see the battery state of health, it will be decreasing and it will be regenerated. So yeah, this was my internship project which I did at the real-time EV dashboard. This completely gives the idea about the ADAS working, EV dashboard, and incoming obstacle warning, and many parameters. Like everything I have included, like what are all the new things to be added the in the monitoring dash system. So yeah, I would like to thank the Emertxe Technologies to giving me more idea about the embedded C and the dashboards, EV ADAS, how it works. I basically got more knowledge about the how the system works and learned more about the warning ADAS systems. So yeah, this was my project and this is the output of my project. So thank you for giving me more knowledge and information about the ADAS systems and the EV dashboard simulation. And I learned more about the embedded systems and the new usage of the softwares, the STM32. So thank you team. Thank you for giving me this opportunity. So thank you.